It's time now to look at another variation on the Atwood machine. This one's a little more difficult due to the way this string wraps around this other pulley here. So we've got a fixed pulley. This is attached to the ramp. We have what I will call a traveling pulley that's attached to mass B. Mass B is free to slide up the ramp. And this will be the source of the difficulty for this problem. Suppose that we're given the value of each mass. We also know how steep the ramp is, and we know the coefficient of kinetic friction between this block and the ramp. And it does matter which direction MA is moving, mass A. If mass A were moving down, that would imply that mass B is moving up the ramp, because we're going to pretend that the string can't stretch. If mass B is moving up the ramp, then the kinetic friction would have to oppose the motion of mass B, and it would point down the ramp. On the other hand, if mass A was moving up, mass B were moving down, the kinetic friction on mass B would have to point up. So that sign change is going to affect your Newton's second law. If the forces on your mass change, so will the acceleration. So the value of the acceleration, which is what we're looking for, we'd like to know the acceleration of each mass. That acceleration will depend on which direction the masses are moving. I don't think that would be the case if you took friction out of the equation, literally out of the equation, but we do have friction, so we have to account for that. As usual, for now, we pretend that these pulleys are massless and frictionless. In real life, if this pulley has mass and there's friction in the bearing, it's going to take some torque to get it to turn. And that means the string on this side would have to pull harder than the string on this side. Let me say a couple things about the way I've drawn this here. This line segment here just means that think of it as some sort of bracket attaching mass B to the center, to like the axle of this pulley wheel. By the way, I think the actual wheel of a pulley is called a sheave. The pulley itself, it's like the combination of the wheel and the string. It doesn't refer specifically, the word pulley doesn't refer specifically to the wheel. Same thing over here. This string wraps around this pulley, then it wraps around this one, and think of it as being attached at the axle here. So this string or this line does not in any way suggest that the motion or the turning of this wheel is being impeded. It just passes around the outside of the wheel and attaches at the center. I hope that's clear. Okay, we could label a coordinate system. I could say this is the positive y-axis, x-axis here. Over here, I could call this the y-axis and this the x-axis. Actually, I probably should. And, well, what's the simplest way to do this? I'm going to stick with that rule. Whichever direction you expect something to accelerate, call that the positive direction. So for mass A, we're told that mass A is moving down, it's falling. This is slightly ambiguous because wouldn't it be possible for this mass to be descending but slowing down? If it's descending, the velocity points down, but if it's slowing down, the acceleration actually points up. So I really do need to make an extra assumption about the direction that it's accelerating. They just tell us that the mass is falling. I'm going to take that to mean that the velocity is downwards. I will also assume that this thing is accelerating downwards, which means this one would be accelerating up the ramp. Let's jump right in with a free body diagram. We'll start with mass A. Here's a dot to represent mass A, so I don't have to draw the block. Gravity pulls down, mass A times the free fall acceleration, and then I will draw a shorter arrow upwards and call that the tension. I only see a single string here attaching to mass A, so there's just one tension. And I will call this the positive direction and say mass A times gravity minus tension equals mass A times the acceleration of mass A. And you're going to see that in this problem, we actually do have to distinguish these two. Previously, we related the two accelerations by noting that the string doesn't stretch, and that means the velocities or the speeds have to be the same, and hence the magnitudes of the accelerations have to be the same. In this case, we will not arrive at the same conclusion. If I'm interested in solving for the accelerations, one of those accelerations shows up in this equation, but I cannot solve for it yet because I have this additional unknown t. So if you look at what's given in the problem, this one equation has two unknowns. I have to continue writing equations. I don't think there's any other equation we can get from mass A because nothing interesting is happening along the x-axis. Darn gravity. I think I'll do mass B down here. And this free body diagram is a little more difficult because there are a number of forces acting on mass B. Okay, here's a subtle point. Because this traveling pulley is attached to mass B, when I write F equals ma, I'm actually looking at not just the mass, but the mass and the pulley and the little bit of string inside this bubble that I've just drawn. So remember, we're going to pretend as if this pulley has no mass. The same goes for these little pieces of string. But by drawing this bubble, I make it a little easier to identify the forces acting on everything inside the bubble. We've obviously got gravity pulling down on mass B. We have the ramp itself pushing on mass B. In which direction does the ramp push on mass B? Well, if mass B is traveling this way, I would say that the force of the ramp on the block points in this direction because it's got a component down the ramp, that's what we call friction, and then it has a component normal to the ramp, that's what we call the normal force. But don't forget, those are two components of a single interaction between the ramp and mass B. Okay. Normal force, which is normal to the ramp. I'll start by drawing gravity straight down, mass B times G, but I have to resolve it into components, one of which is normal to the ramp surface and the other is parallel, points down the ramp. And you've seen this so many times, I hope you remember that if this angle is theta, so too is this angle. Of course, I could use sine and cosine to turn the hypotenuse, mg, into the components that are perpendicular to and parallel to the ramp. Have I gotten everything? No, we have to account for friction, F sub k. Anything else? Well, if these were the only forces on mass B, wouldn't mass B be accelerating down the ramp? We know it's accelerating, or I'm assuming that it's accelerating up the ramp. And that would be the tension that's producing that acceleration, along with the other forces. And this is the first time you've seen this. Yes, there's a single string here that's wrapped around, but what you have to ask yourself is how many points of contact are there between the string or the rope and everything inside the bubble? And I see 2 points of contact. The tension is being applied here, and it's also being applied here. So I could draw 2 vectors here and label them both t, or just draw a single vector and call it 2 times t, t plus t. Those are all the forces that I can identify. And now I probably do need to label my axes here because I will have to write Newton's second law twice. All right? What would be the best choice? Well, since I expect mass B to go up the ramp, how about I call that the positive x-axis and the perpendicular direction is the positive y-axis. Let's start with the axis normal to the ramp, which is what I've called the y-axis. So I'll say sum of the forces in the y direction. Of course, I'm talking about the sum of the forces on mass B and its proprietary pulley. Mass B times the acceleration of mass B in the y direction. Okay, so the notation's getting a little challenging here because I've used a single symbol to refer to the acceleration of mass B because it should be obvious from the diagram that mass B's acceleration is in this direction. Right now, I'm talking about the acceleration of mass B in this direction because I'm applying Newton's second law along the normal axis. Hopefully you recognize that this acceleration should be 0. There's no reason that this block should be accelerating off the ramp or into the ramp because these strings are pulling parallel to the ramp. So it's up to you to recognize that this acceleration is 0. The sum of the forces along the normal axis, the sum of those forces needs to be 0 for mass B. Because this is the positive direction, I'll give n a plus sign. I'll give this component of gravity a minus sign. And I think that's it. We don't have to worry about these forces because these are orthogonal to the normal axis. So they have no components along the normal axis. And I would say n minus, well, this is the adjacent side of this right triangle. This side is adjacent to theta. So I would use the cosine. Minus the weight of mass B times the cosine of theta. That's got to equal 0. And this equation tells us that the normal force is not merely the weight of mass B, it's the gravitational force on mass B times the cosine of theta. This result shows up in a lot of problems. I would memorize it. I think it's worth memorizing it, but you don't want to just quote it naively because sometimes there may be additional forces along this axis. What if there was a third string that was kind of lifting up on mass B, or a bird sitting on it, or somebody pushing down on it? If another force appeared on the left side of F equals ma, then when you solve for n, you would have something else over here. So you don't want to just assume that the normal force for an object on an incline is mg cos theta. It could be a little more complicated than that. Well, now that we know what the normal force is, we can immediately conclude that the friction force magnitude, the magnitude of the kinetic friction on mass B is mu times n. That's going to be mu mg cos theta. As soon as you have determined the normal force, you now know the kinetic friction. Because in this class, that's the simple model that we always use. I can't think of a single exception this semester. We always use that model for calculating kinetic friction. Just take the coefficient, multiply by the normal force. What are we going to do with this? Well, it's probably going to show up in this equation. Remember, we're trying to find these two accelerations. We'd like to know mass A's acceleration, and we'd like to know mass B's acceleration. And I have not yet written an equation that has the acceleration of mass B in it. Or really, I'm talking about the acceleration along the x-axis. So let's go now to that equation. F sub x equals mass B times the acceleration of mass B in the x direction. Okay, so I'm being really careful with the subscripts here to remind you that we are applying Newton's second law along the x-axis. But here's where we can go ahead and recognize that the way the problem was phrased, they're using this symbol for specifically the acceleration of mass B along what I'm calling the x-axis. So I can just simplify my notation here and just call this A sub B. Okay, what forces do we have? I've got, since I'm calling up the ramp positive, I've got two tensions in the positive direction, and then minus, well, let's do this first. Take the component of gravity that's down the ramp, minus mg sine theta. This side is opposite theta. And then lastly, don't forget about the friction. We've already solved for friction in terms of the normal force, minus mu k mg cos theta. And do I set that equal to 0? That would only be true if there were no acceleration. The sum of the forces along any axis is only 0 if the acceleration along that axis is 0. But we are expecting an acceleration. We don't expect these forces to balance. We don't expect them to sum to 0. I will set that equal to mass B times the acceleration of mass B. See how I'm just relabeling this as A sub B? Okay, now I'm going to underline our various unknown quantities. And I took a cue from some other Atwood machine physics person on YouTube who uses these bold markers. Let me look at all three of the equations I've written and underline the unknown quantities. I don't know the tension. I don't know the acceleration of block A. I don't know, well, that's the same unknown. The tension is the same unknown as it was in the previous equation. And I don't know the acceleration of mass B. So I don't want to double count these two. That's one unknown, two unknowns, three unknowns. I have three unknown quantities. I'm only really interested in two of them. Because the problem was asking for the acceleration of each mass, I'd like to find this quantity and this quantity. But if you've got three unknowns, you're going to need a minimum of three equations. Maybe you're thinking, we did write a third equation, this one. And not really, because this equation doesn't contain the unknowns that we're interested in. You need three equations in those three variables, and we've only written two equations that contain those variables. So we need a third equation. And this is the theme throughout the semester. When a problem is, when you're confronted with the problem, one of the first things you probably should do is figure out what are the unknown quantities that you're looking for, count those quantities, and then that's the same number of equations that you're going to need, and you should just figure out where will you go to get those equations. And it's usually F equals ma. Well, we've already exhausted the possibilities with F equals ma because there's only one relevant Newton's second law equation for mass A, and we've already done the two equations for mass B. There's no sense in looking at the sum of the forces along the z-axis because this problem is two-dimensional. Where do we go to get that third equation? It's an acceleration constraint. That's your other resort for these Atwood problems. Is there a way that you can relate these two accelerations? Maybe these two are the same, the acceleration of mass A and the acceleration of mass B, or perhaps they can at least be related. So this might be the trickiest part about some of these problems. Here's how I think about it. If mass A were to drop by 1 foot, if it falls 1 foot down, then 1 foot of rope has to appear over here that wasn't here before, right? You've got a certain amount of rope here. If mass A drops by 1 foot, you've got 1 extra foot of rope that just appeared. Where did that rope come from? Or string, where did that string come from? It had to come from over here. Now, if you need 1 foot of rope to go from here to here, do you see that each of these would only have to shorten by half a foot? If mass B moves up by half a foot, this string will get shorter by half a foot, this string will get shorter by half a foot. That's a total of 1 foot of rope. Where does that 1 foot of rope appear? It can only appear over here. To me, that's the simplest way to figure out the acceleration constraint. If this thing only moves half the distance that this one moves in the same amount of time, wouldn't that be half the speed? And you could take another derivative and you'd be talking about half the acceleration, or at least the magnitudes of the accelerations. So I think what I've determined is, I'll write this equation here, the acceleration constraint. This is the other place you can go to get your equations. At the very least, I can say that the magnitude of mass B's acceleration is only 1/2 the magnitude of mass A's acceleration, because in equal times, mass B will only move half the distance that mass A moves. However, because of that rule that I'm following, remember the rule that tends to eliminate sign errors. Whichever direction you expect your objects to accelerate, call that the positive direction. That tends to eliminate the liability of messing up your signs here. So it's not just the magnitudes, the signs are also the same. And there's my third equation. So let me number these. I can call this my first equation, the acceleration constraint. And then I've got this equation, which comes from looking at F equals ma applied to mass A, and then lastly, this equation. I could rewrite this equation if I wanted. Let's see here. Do I want to do that? I'm trying to solve this in the simplest way possible. Ultimately, we're interested in the accelerations here. We're not interested necessarily in the tension. So I need to eliminate the tension. Now, if I could turn this 2t into a t, I'd have a plus t here and a negative t here. I could add these equations and the t's would be eliminated. Well, notice if I multiply this entire equation by 1/2, I would have a 1/2 AB. Actually, that's no good because AB is already 1/2 of, well, I suppose that would work. Let me do this. I'll just rewrite A sub B. I'll substitute. A sub B is the same as half of A sub A. So I would pick up a 1/2 out front, mass B times the acceleration of A. That gets rid of the acceleration of mass B. Now I've got two unknowns in these two equations. So I've used one of my equations to eliminate A sub B. I have two equations and the same two unknowns now. Now I'm going to eliminate T. I'll do that by saying, take equation 2, and I like to put little circles around here to indicate that I'm adding equations, not just numbers. I'm not adding the number 2 to the number 3. So I'll take equation 2 plus 1/2 of equation 3. This is my method for solving for the unknown that we're interested in. You could do it however you want. Like I've mentioned before, you could just keep using back substitution. You could use an augmented matrix if you want to be really fancy. I call this linear combination. I think that's how it's commonly referred to. Okay, when I add the left sides, remember this 2t turns into a 1/2 of 2t, which is just t. T plus negative t, that goes away. And I've got left over mag minus 1/2 mass bg sine theta. Don't forget the 1/2 mu mg cos theta. I ran out of room, so I'll set that equal to, and then on the right side, don't forget the right-hand side of equation 2, mass A times the acceleration of mass A. And then if I had multiplied this by 1/2, well, I've already done that. No, I haven't already done that. Don't be confused like me. This is already 1/2 of acceleration of mass A. I'd have to multiply by another factor of 1/2, so I would actually have 1/4 mass B times the acceleration of mass A. This is the equation that I'm solving for A sub A. That's the whole point here. Now, you may be thinking at this point, there's a lot of symbols here. Maybe it would have been easier if I had actually plugged in numbers already, and now I would be working with numbers. That's really a matter of taste. Personally, I like to do as much algebra as I can and plug in numbers at the end. Sometimes it's really not worth it. Sometimes the algebra becomes so onerous, it might be better to calculate individual terms. In this case, I don't feel that way. I could factor out A sub A here. I'm going to flip the two sides of this equation and do some factoring. So on the left side, I've got acceleration of mass A times ma plus 1/4 mb. That's this put onto the other side. And I'll set that equal to, well, what could I factor out here? Each term has a g, so I can definitely factor that out. But you'll notice these two terms also have a factor of 1/2 mb in common. So I could write this as ma minus 1/2 mb, and then in parentheses I would have the sine of theta plus mu sub k cosine theta. This might be the cleanest way to express it. Hopefully I haven't made any errors here with factors of 1/2. And lastly, we can simplify or just divide, and we get one single formula. This is still going to be a pain to evaluate with your calculator. And I suppose if you've got a TI, you could just plug the whole formula in all at once. I'm not going to evaluate this for any particular numbers. I'll just move on and look at some other problems, but it's kind of nice that you can get a single formula for the final result. Can we look at this and see if it makes sense? What sort of acceleration would we expect for mass A? That's what this formula tells us. Well, what if this thing were extremely lightweight, just a couple grams, and this thing was a metric ton? Wouldn't this fail to slow down mass A by any significant amount. If this is a metric ton and this is just a few grams, this would practically be in free fall. So if I go back to my formula here, if MB was really small, maybe you could just ignore this term, and you would have merely MA over MA, which is 1, and the acceleration would be G. So that much makes sense. Beyond that, if I want to check to see whether this formula is reasonable, I don't have much intuition about that. I do suppose, or I figure, what's the word I'm looking for? If this angle went to 90, this would start to look a little bit more like a regular Atwood machine. Maybe we'll look at that problem in the future, a simpler problem, and see if the result that we get for that problem is contained within this more general result. Don't forget that once you have evaluated this number, how do you go back and finish answering the problem? Because the problem asked not just for the acceleration of mass A, but also for the acceleration of mass B. We determined that mass B's acceleration is 1/2. So I'll just rewrite that here. Just take half of whatever number comes out of all this, and you would be done at that point. If you also wanted to know the tension in this string, you could just go back to one of the original equations that you had written. I think this one would be the easiest. After you had calculated the acceleration of mass A, plug in all the numbers that you know, and you can solve for the tension. So this is a more challenging problem. The extra little twist there is the acceleration constraint, and it takes a little bit of thought to determine that constraint. I'm going to say that a problem similar to this would be fair game for your exam. The Atwood machine, the regular old Atwood machine, that's too simple for an exam problem because you've seen it a number of times. So there would have to be some sort of variation there, something like this. Get some practice with these acceleration constraints. There are a couple problems at the end of your chapter with acceleration constraints similar to this one. And I will also look at some more examples here.